Hello, everybody, and welcome to this ESA BIC Nordic Academy Christmas special. I see people are still onboarding the Zoom call, but we'll get started. We are fortunate today to have Professor John Leif Jørgensen from the Technical University of Denmark as our keynote speaker. And we are fortunate because John has a lot of experience in the space sector for a number of years. And he's one of the most visionary people that I know of, at least, in the space ecosystem in Denmark. So today, John will use his visionary superpowers to look into the crystal ball of new space and provides you guys with a sneak peek into the some of the emerging commercial opportunities in orbit. And for those of you who don't know John Leif Jørgensen, I can just briefly introduce him. He's a distinguished full professor in space technology at DTU Space at the Technical University of Denmark. John and his team of researchers and technicians have developed space instruments, which have flown on more than 100 space missions. And he has also received numerous awards from both NASA and ESA for his contributions to space technology and space science over the years. So in this Nordic ESA BIC Academy Christmas special, John will provide us with unique and also concrete insights into how innovative applications of space technology can exploit some of the emerging commercial opportunities in space. So welcome everybody, and especially a warm welcome to John from ESA BIC Denmark. Please, John, the floor is yours.
Okay, thank you very much. I'll try to see whether I can master the technology here and get shared my screen here. Let's see. Does it work?
Yes.
Okay, so thank you for having me to this academy. It's an important subject, and there's a lot of unharvested potential in the space sector with the growth rates we are seeing these years, but it's also a difficult market that has to be attacked on a structured way, I suppose. So what I've been trying to do is to look a little into the future, just to give you a feeling for what I see is coming in the coming years. And let me start by. Let me see whether I can do anything. Okay, this is just to show that my own career in space started back in 1983, where a colleague came into my office and asked me some questions about how to use a camera in space, and that slowly developed over the years. It took me about 10 years before I had the first flight system that could be sent into space. And that was done as a side to my normal research. But after 1993, where we got the ESA project funded by the Danish government, it actually speeded up. And as Sune already mentioned, I'm now on more than 100 space missions with our equipment in very, very different applications and places. Here's some of the satellites over the years that we have been catering to. It's not up to date though, because it's only up to date as of last year, but doesn't matter. It's just added some 20 more satellites this year. As you see, we are on Mars. We are in orbit around Mars. We are in deep space. We are in orbit around Jupiter. We are at the International Space Station and tons of low and high Earth orbiters. Again, let me see whether here. So the first question you could ask yourself is new space real, or is it just the same thing as we always did? And I see only one real big difference between the two. And let me just run through the way the cost structure of a standard space mission is. I call it old space, and in contrast to the new space. But start with the old space first. The concept phase of an old space mission is typically where the ideas are brought from science fiction into at least some technology that is flyable. Very little money is used in this phase. It's done kind of more or as industrial efforts from around. There are a lot of support programs that you could use, ESA BIC being one of them, but also ESA has several others if they are for old space missions, the bigger ones. So a few percent of the total cost is spent in the concept phase. Next comes a phase A. That is where you have to prove that your TRL is large, your technological readiness level is larger than like 4 or 5. That means that you have a demo ready in the lab. Then comes phase B1. That is phase A. Many missions actually stop after phase A because they become impractical or too expensive. But the few that actually do survive will typically get into the B1, where you detail a flight critical components to such a level that people believe in that they can be built. Then come phase B2 and C, where you build the actual spacecraft. And again, here the running cost is typically some 30% of the total mission cost. Phase D, that is the testing of the equipment and making it flight ready. That's a relatively expensive test, so also here is some 15% spent. Phase E, that's the running cost of the mission once in space. That is the operations of your space asset after you made it. Many of you that starts in space will actually start seeing phase E missions where you work on other people's technology, and again, some money spent there. The agency overhead on these missions is about 100%. That is, they double the cost to the taxpayer. So whatever you get for the mission, the agencies, that would be NASA or ESA, will suck up some of the juice. The launch cost for these missions are typically about 30%. So that means that the total cost is something like 230% of what you think the mission cost is. That's also one of the things that is kind of hidden. You don't see that as a standard customer. It's just there. New space is almost the same. Here, the concept phase, usually in new space, people try something that is very different from what has been done before. And that means that the risk and also the work associated with this, rather than having an evolution of a technology, it's actually a revolution that takes place. So here, the mission costs are quite high, but it's actually the phase E where things are violently different. Here, you have to think about, you have a satellite, and if it's a CubeSat, like the little one up at the top here, Robert Twiggs originally dreamt up this concept of the CubeSats to make a standard for space use. The phase E actually is the most costly because you have to man the station, you have to have an antenna system, you have to take the data down, you have to process it. If you don't, the mission is actually just another wet brick in space. So here is something that you really need to look out for when you talk about new space. I'm just trying to argue what's the difference between what most people think of as new space, that is small, cheap, fast missions. Again, the agencies will still take their 100% as overhead. And the launch is almost the same as the actual space segment that you build. So here you're at the 300% for the entire thing. But the most overlooked phase is the phase E. It's very hard to get money to run such a mission. If you think of, I gave some examples here. I put James Webb, everybody knows that one, I've heard of it. It's the most expensive space mission to date. It's a fantastic cost overrun, and everything there is very expensive. It's an old space mission, and it's built the way that you see up there. The middle one is something that is a compromise between the CubeSat of Robert Twiggs' original concept and the JWST. Now this is a JPL mission which was launched by the Artemis 1 as it went out to the moon, and it's actually a solar sail mission where they try to test solar sail techniques for the future. This one has not been cheap. This is not something that is like anything CubeSat-like. It's small, yes, but it's very, very expensive, and it's also having running cost that compares to what I would call old space missions. So I really do not know whether a new space sector exists or whether it's just new uses of the old space. And I just kindly ask you to remember this as we go on. So what's it all about then? What goes on? We came from a technology that you see up here to the right. Is a motherboard for a computer, which is probably 10 years old, or not, even less maybe. That transited into a modern technology, which you see in a cell phone to the lower right. The cell phone has a higher processing power than the motherboard used to have just 10 years ago. That technique has been brought about by a further miniaturization of electronic circuits, and also a trend towards what is called threshold voltage technologies. That is very, very low drive voltages and thereby low power consumption of the devices. It has been necessitated, otherwise you couldn't build cell phones. But the cell phones today stand as the absolute high watermark for modern electronics. It's very, very hard to beat that, because you have something like 3 billion cell phones built every year. That volume is unbeatable. And that means that the technologies that sits inside this one is actually driving the technology of any other application. In this case here, space computers cannot be directly built based on the cell phone technology, simply because the cell phones would die from the radiation in space very fast. Another change that has come about is the modern production techniques. We used to have turbines like the big one I show you there. They become smaller and more powerful and more lighter and I'd not say cheaper, but at least the efficiency of a turbo pump these days is coming up, and that's one of the drivers and one of the possibilities that makes the new rockets that you see all around the world a possibility. These technology changes doesn't come from space, the space sector itself, but we can utilize these, and they open up. Those are the guys that enable the new markets that you all have to look into, because if we can get a bigger computer in space, then we can also make more powerful onboard processing systems. And what people are looking for there are the two A's. The one is the autonomy. Onboard autonomy is everything. I'll get into that deeper a little later. The other one is artificial intelligence, which is also enabling new services on board. But we also do get new sensors all the time, and I'll give you a few examples when I get into the more concrete examples at the end of this. New materials, and we get rather complex systems. So technology base is changing, and that drives all the other things. It comes with opportunity. So where is the marketplace? This is something that you all have to look for when you try to build yourself a business. The first one is that what do we know of as a marketplace? The first one to be visible to the world was actually the launcher market. The reason that was so visible is because launchers are nice to look at, and the medias love them. So when SpaceX launched their first Falcon 1, it was of course, they never do anything meaningful with that. Now they launch a Falcon 9, something like every 2 or 3 weeks on average. That's a feat never been reached before by any company. So you could say, what was it that they did here in the launcher market? They realized, well, there's a lot of guys that wants to have stuff put into space. We need to do it cheaper than everybody else. Elon Musk originally claimed that he wanted to launch at 5% of the cost of anybody else at the time. He stopped at 30%. That's where he is now, because nobody can reach him there. They are coming though. I mean, in a few years' time, there will be many alternatives. And in 10 years from now, it's not certain that Elon Musk and his SpaceX is going to be the world leaders. The thing is, they are old-fashioned, they are polluting, they have a very low fuel efficiency, the ISP. So it's really not a modern technique. What Elon Musk did is he took technology from the 1960s, built a motor around it, the Merlin motor that he is workhorse now. Then he actually did something brilliant. He put 9 of those together. That's the reason for the Falcon 9. So Falcon 9 is a rocket which is based on 1960s technology at the motor stage. He has a very low pressure in the combustion chamber, means low efficiency. The reason for that is that it's reliable and it's reusable. So he can reuse the motors. But several missions he has launched now where one of the motors did not work. If you only had 2 or 3 motors, as many other missions do have, it would be a mission failure. He can actually fly with 8 of the 9 cylinders in use. So that's one thing to think about. His thinking here was, let me do it reusable, let me do it safe, and let me do it cheap. And still remember, there's in a Falcon 9, there is about $300,000 worth of fuel in it. It's not really expensive. It's not the fuel that drives the cost of the $85 million that the launcher itself cost. So technology is everything, fuel is nothing. That was his optimization. He, of course, seized a market that already existed. He just made a cheaper truck to go to space. So in a way, you could say he just used or misused a marketplace that already existed, which was catered to by other guys like Lockheed Martin or Northrop Grumman, Boeing. And these guys are coming after it now with new launchers. But that's a marketplace I would rather not go. I think it's rather already red, if it's not all black ocean fishing here. So, and also it takes big money to do this. It's not really something for the Danish infrastructure. Then there are standalone missions. That is entire satellites where you do a service, you build a service of kind. That is again, a satellite will cost somewhere between 100 million euros for the cheaper ones, up to several billion euros a pop. Again, this is not something you will do in Denmark and as an upstart. Space Systems, on the other hand, is certainly a place where you can play, and I will focus on that sector. I suppose none of you are planning to make a billion euro business just today. You may do it after some years, but not today. So let's focus on the Space Systems. One of the things you can do there, let me just give you an example. You see that to the left, that's the NASA's distributed antenna system. By putting some small CubeSats out and let them act together, they can form a radio with a fantastic aperture, meaning that they can actually have a very directed antenna. It's not obvious that small, stupid single satellites can do this, but if they act together, they can become way more intelligent. There's a lot of examples of this. Many proposals I see every year for this kind of systems where you distribute the intelligence between small other sectors. In ESA, ESA's little discovery plan for CubeSats, they also show you what they have in mind in terms of uses of it. You can always read that slide later. I suppose sooner you will distribute this after this year.
Yes.
The next thing is downstream, upstream processing. Upstream processing has become relatively important because just 5 years ago, a megapixel image was state of the art. Now it's 100 megapixel, and there's no way that you can download all that data from space. So you need to select the data, you need to process it heavily on board. And right now, the big thing is the AI methods to compress, filter, feature select stuff that you want to send down. Just consider that you build yourself a satellite. It could be a 500 kilo satellite with an antenna of 1 meter, infrared looking, and something goes on in a country near our borders and that you would like to report down. If you want to take 100 megapixel down, you cannot do that as a video, that's for sure. There's no bandwidth, there's nobody having that kind of bandwidth, so you need to limit yourself. You can do that by upstream processing. We happen to work a bit with a company called Maxar on other missions, and they do exactly this. They actually down select the data in space to send enough down of the relatively high quality data that you all saw of Ukraine earlier in the present crisis there. So upstream processing has a lot of potential. It could be that you are looking for uplifting earthquakes. It could be other kind of disaster monitoring. But all these processing has to be done to down select data. I'll give you an example of how bad this is for us. Downstream services is also a sector that is somewhat easier to use. If you look at how Google have integrated everything into their maps device here, it doesn't need to be like that. But you could imagine that Flight Radar 24, if you ever tried that app, gives you a good example of how you can integrate data from elsewhere. The data that comes from space are actually not easy to access. The problem is that they are on public data servers, all right, but they are hard to interpret. So those that can interpret the data and bring it in a format that is useful for the general user has a fantastic opportunity to make a business for themselves. So the downstream services are something you should not overlook if you are an app developer. It's there's a lot of things that can be done here. Lots of stuff. I mean, everybody is talking about space weather these years. We do have the measurements of the space weather. There are no integrated services that you can use on your cell phone to get instant or near real-time data. We have it for weather, but not for space weather, even though the data exists. So why is it that .no or DMI.dk can do this on an app on your phone, and nobody does that for the space weather? At least a lot of people would like to know when there's the next polar light or aurora will be visible from Denmark. So I'm just saying that there's a lot of potential here that's untapped totally. It's a market that's all blue. So I'll say the upstream processing, we're talking about AI method, or at least something that's highly selective so that you get the right data down, is worth a lot. Space systems of smaller units and downstream are all accessible for people like industries we have in Denmark. So what's the present status? I'll just take you the example of rocketry. Again, Elon Musk, because it's an established fact and we have a track record there. To the lower left, you see a graph that's hard to read the legends from, but it starts in 1960, 70, 80, and 90, and 2000, 2010, and stops at 2020. And the number of launches you see here is they come from different nations. Most of them are military. So, oh, that was too fast. But you see that they actually peak here around the 80s, and they were all of the kind where you have military applications, and then it dwindles down to the average that we know of these days. If you look at it to the right, they are divided up into sectors, and the green one here is obviously Falcon 9. So Falcon 9 is just to show that it really takes off, and this year it's just up here. It's just to tell you that Falcon 9 is launching as many rockets every year now as the Chinese are, as a company alone. It tells you that there is a marketplace. It's not just going to go somewhere else. And it's not just me that says this. In the EU, it has been estimated that this year, that's 2022, I'm referring to, about 10% of everything we do in our GDP, 10% has actually a space component based. That means that it's not entirely space, but it is highly integrated with space services. This is actually an important takeaway for you guys here. And it's estimated that we have about 230,000 FTEs in the conventional space sector in Europe. That's Europe. Denmark is about 2% of the EU. So you can scale that down to get what our share of this is. We actually under that norm. We are not living up to the European standards, mainly because Denmark is spending too little on the ESA sector. But this is expected to grow almost doubling to 25. That's in 3 years' time from now. So it's that means that there's expected to be a growth. We should try to get some of these. I'm just saying that this is EU's expectations, and there's some of the fun stuff over here. Is that what are the expectations in the sector, and it depends a bit who you look at. What is the total value of the market and stuff? But what you really should look into is, of course, the CAGR. They think that we could reach something like 10% and maintain that. It's about the fastest growing sector then. I think it's worth a thought too. So it's you're not wasting your time if you are doing this, but you have to be careful what you're doing here. Now, let me give you a little feeling for what is going on here in the space sector. And here I'm just looking at the trends. So I just looked at the marketplace that I know of, and what is right now hot with NASA and ESA. First one is refueling in space refueling. That is, a tanker spacecraft goes to another spacecraft and refuel it, so its precious cargo can go elsewhere. It can take many forms. Sometimes it's just a telecom satellite that ran dry. That's, for instance, Northrop Grumman is trying to do that. Go out to the DTO to geo orbit and refuel some of the relatively good telecom satellites that are already up there. Such a telecom satellite is maybe worth a billion euros, something like that. So if you can refuel it, there's a profit margin there. That's one of the hot things right now. But it's also to be able to refuel a big vessel, for instance, going to Mars or elsewhere. That's the other thing. And just to see, are we the only ones that are saying this? Not really. The Chinese are right now planning to make a spacecraft 600 meters long. You can imagine what that should be used for. I mean, it dwarfs the International Space Station. So it's just to say that there's something there. In situ resource utilization is everybody's business. If we can use stuff that is produced locally, we should do so. And the first lunar landers, both from ESA and from NASA, will actually focus on using, in the first order of the regolith to make housings and stuff. Later on, water. And that's, of course, another one there. Another thing that in the locomotion thing is, of course, RTGs, radiothermal generators. The problem with these is that it's not a good technology for Denmark because we do not have any production plants for isotopes. And so far, all RTGs has been co-produced with weapons-grade plutonium production. And this only takes place in a few countries in the world. So you can imagine that there's a very limited market. So everybody's trying now to find better ways of producing the plutonium needed for these batteries. But it's really, really needed if we want to go anywhere. You cannot build a base on Mars without this. And then improved ion drives. I'll give you an example a bit later. The ion motors are the name of the game. It offers potentially something like 10,000 seconds in ISP compared to the 200 to 300 of conventional rocket motors. So an efficiency that's out of this world is, of course, worth it. New launchers, small and super heavy. The super heavy ones, I guess we leave to NASA. The small ones could be European as well, but the problem is nobody can make a motor that is efficient enough to launch you directly into space unless you're air breathing. And that means you start with an airplane type thing. And there's a gazillion of attempts to design these such systems by all the big airplane companies and stuff of the world. Problem is that this technology is not easy because the motors that you use on board has to run in the standard turbofan domain going up to maybe 20 kilometers, then change to ramjet going up to 60,000, and then scramjet the remainder of the way, and then rocket at the end. So it's this kind of motoring is difficult. Then, but theoretically, it's possible to do this. Now, the reason why I mention these things is not to harass you or give you or to take the spirit out of you. It's because any technology that's around this, I'll get back to this in a bit, any technology that's around this is actually sellable. And it's a relatively easy entrance into the market because the big guys will desperately want to get the test equipment that it takes to make these things here. And that goes also for the new mission concepts. Formation flight. Formation flight comes in two different flavors. The one is that you have global network, like the telecom satellites or the weather satellites. But you also have another kind of formation flight over here. This is the Aqua train. It all started with a mission called Aqua. That's why it's called the A train, Aqua train. And Aqua, had a very powerful radar antenna, which other guys down the same orbit could pick up and thereby get a much better resolution than what Aqua could with its own antennas. And it has since been a train, and there's I think right now there are 13 satellites in that constellation. They're picking up various signals, and that's also sellable. Even here is one of the few places where CubeSats are doing a valuable contribution to the world's knowledge of our Earth. So anything that can support constellation missions is also a blue ocean these days. How do I go when I decide what technology to spend our measly money on? I always look at what the other guys, the big guys, NASA and ESA, is on the outlook for, because whatever NASA and ESA does is pretty much the essence of what is technologically possible. So NASA gives you here, what are they after? Any kind of autonomous systems, markedly robust autonomous systems. It's not a Tesla that runs into the side of a car. This is something about making things almost animal-like autonomy. That is, you have to use sensor fusion to do this. You have to use more than one sensor. You always have to control what you're doing. The other one is efficient air transport systems. Of course, that's not really Denmark. Space and hypersonic technologies. Hypersonics is a big thing right now, as you probably learned in Ukraine. Electric propulsion, they like to have, and then any kind of avionics and instrumentation technologies. Out of these smart sensing and sensor developments here, supersonic technologies, flight and ground experiments, and virtual augmented reality. I'd say autonomous systems, avionics, and instrumentation, flight and ground experimental test capabilities, and virtual and augmented reality are natural for Denmark, the Danish sector. If you could do something here, just imagine if you are the ones that make a good test system for a new iron motor. It can be sold to everybody that tries to make this. So that's why I'm saying that it's an easier way into the market. ESA is a little more scarce with what they show in technology. They have different things like sensors on a chip. They have various momentum management systems in microscopic scale. Well, I mean, fist size systems. Cryogenic pumps. That's one of the things. I mean, we have had refrigerators for a century now, and we are still not capable of making a reliable cryogenic pump. And you could imagine that there must be some money to be had if you could do this. I do not say it's easy. There's just a lot of money for those that can do it. So maybe there's something for Grundfos or Danfoss to look into there. So that's how I do it. I look at what are they looking for in terms of technologies, and then I look at what they are asking for inside the missions. So let me go one level deeper. And this is now we are getting to where I'm really working hard. That's my expert field, I would say. New materials. one of those, I mean, everybody knows 3D metal printing these days. You can do mysterious designs with it, but it's expensive. So why should anybody care about making metal prints? There are actually 3 reasons to do so. The first one is that you can make structures with internal holes and stuff, things that are simply not possible in subtractive manufacturing of standard milling and machining. So you can actually make structures that are hyper complex and that are really optimized in mass to volume or functionality. The other thing you can get is you can try to get make structures that are stronger than possible. That means that you can make new things with it. Lastly, you are also capable of controlling its mechanical properties better. Nano and other of these technologies, I give you an example here with the Vanta Black. This absolute black material, it's blacker, 10 times blacker than black paint, 10 to 100 times blacker. It really is fantastic material for use in space as well. It's carbon-based, so you have to protect it against atomic oxygen. But if you can do that, then it's actually your material to use in space, either for thermal or for optical properties. One of the things that I've found to be limiting the satellites we do these years, those that right now doing, is actually the lack of really stable structures. Anything change its shape with temperature. And that means that a telescope is no better than its best temperature compensation. It's a terrible thing to have. So the performance of a spy satellite these years are actually limited by the ability to make the mirrors accurate enough and stable enough. Here, there's an enormous effort going on at various labs and structure and places to make zero expansion materials, either metallic or crystalline or composite, and with some advances, but still this is the limiting factor for spy satellites. So imagine there's a marketplace waiting for those that succeed in making a zero expansion structure here. Another thing that's really hot and coming, and that's in every technology I know of, that's cold atoms. If you chill the atoms, you can get the noise down, and the sensitivity being the same, it means that your signal to noise goes up, typically a factor of 1 million to 100 million times above what you can reach with standard technologies. It means that a simple gravitometer can be turned into the world's most accurate clock, just by doing that. Another one is quantum technologies. Quantum technologies are, they come in different flavors now, but they're one of the first ones that seems to give way to technology is the entanglement, the qubits for unbreakable coded messages. And that's at least something that has been attempted these years. It will just grow. There's no doubt that this is simply the future. So anybody that works inside this also has a chance for that. Another one is silicon and sapphire. The problem with a cell phone, as I mentioned before, bringing it into space, is that it can latch up. And if it latches up, it dies on the spot in a millisecond. So how can we make it immune to this? You do that by putting the silicon, instead of on a copper plate, you put it on a carrier made out of sapphire instead. And this aluminum oxide substrate also has a better compliance to the silicon. So it actually is a win-win situation. The chip will last longer and it gets radiation immune at the same time. So this technology has a lot of potential in it. It's something that's not done much in Denmark. We could, but we don't. The last one on the new sensors things is integrated redundancies. When I last flew a mission to Mars based on our sensor navigation package, we got hit by a heavy ion from the cosmic ray background, and it made a made a bit flip inside an FPGA. Bit flip means that a 0 becomes a 1 or 1 becomes a 0. That's in a processor, you can find that by Hamming coding the signal, data stream. But if it happens in the configuration of a FPGA, field programmable logic array, then you will actually get a configuration change. And in this case here, one data stream stopped, and they had to reset the onboard computer to get rid of this. That's not nice. So technologies that evade this problem in FPGAs are highly sought for. It comes in any flavor. It comes in the design rules, that is how you design and use an FPGA, but you could even imagine that somebody that makes a compiler that builds this into the system. After we learned this about the Mars experience or the Mars flight, it actually succeeded. It was a very successful mission. After the reset, we never saw any of this again, but I learned something from it. You need to build in this redundancy inside the circuitry. The new FPGAs are very, very big, but instead of filling it up with not used technology, it could be used to have, say, 4 parallel processing channels. Then you can make majority voting and always deem one of the process chains out as ill and make your own reset of that chain. These kind of things are highly sought for, and a compiler that does this automatically will be extremely valuable, or at least if you manage these technologies, you can sell yourself or the service to somebody else. So it's just to say that that goes for censoring. The onboard processing is about AI. It's about better compression standards, and it's also about getting inline CRC check on communications, that every message passed between subunits should actually be protected by some kind of CRC. We don't do that. You all know that a level 1 cache doesn't talk to the rest of the world. It just gives you the result and you die with it. So it's this technology thing is I know it's highly technical, but that's what you need to consider if you want to go into that business. Downstream services, there's data interpretation. Also, data archiving is a big issue. There's a lot of money to be had because these PDSs require simply a format of storing the data. Every mission I'm on, I have to store my data, and I have to write a book on how other people can interpret that data. Otherwise, it's just a mass grave. So services here about how to store data and how to retrieve it again, but mostly how to stream the data to users that want near real-time solutions. That's also a big marketplace. So how do you find the new technologies? Here's my little peek into what is hot on the ESA and ESA side these days. ESA just announced that they are going to build a solar farm in space. This could very well be the most expensive, but also the most promising technology humanity ever came up with. Remember, out in space, there's a lot of sun, a lot of sunlight. The sun never sets. You have twice as much light reaching your solar cells and in space. And that means that you can make a solar farm up there on much lesser area, or you can get a much better yield of it. Right now, the technology is about 10 times too expensive. That was before the energy crisis. Right now, it's actually a draw. It's about as cheap to make this in space as it is to produce it on the ground, but that's because it's small scale. So here's a lot of technology, and I'll just remind you, imagine that you have to build a 500 square kilometer solar farm. You need robots that build this. You need robots to maintain it. You need distributed intelligence systems to make sure that you find errors, micrometeorites, for instance, that penetrates and kill a wire. You need to locate these. So the communication systems of this would just be as important. So this technology here could easily become the biggest investment that anybody is seeing. It's risky though, because there's no doubt it will come. It's just a matter of when and which technology will win at the time. I'll just go one level deeper in the next slide. It's just to give you a feel for where we are. And I'm running out of time, so I'll rush. Another thing that's really, really hot now is a refueling concept. NASA has 5 missions right now, refueling. It's coming, and it will stay there. Because we want to go to Mars, we want to pick up samples that we are actually picking up on Mars' surface right now, and we get to these back to Earth to look for signs of life, and also to get modern chemistry advanced on this. So you can imagine that this thing, Mars sample returns, will actually drive the technological development in the next 5 years to get up there. So the next layer, when we talk about solar cells in space, of course there's radiation up there, but you put a little surface layer of quartz glass on top of it, and then you are pretty much protected from the radiation. So the real problem is how to do this. One of the things that we do in space in order to save area is that we use what is called triple junctions. A standard solar cell will usually be sensitive only in the green area here. So here we use aluminum gallium arsenide sensors, which is a standard solar cell here on Earth. But if you want to use the full spectrum of the light, we actually stack 3 layers on top of each other: blue first, then green, and then red. And we make them up of different structures here. And then we get an efficiency in the pushing 40% efficiency. Now, this is easy for you. Everybody can understand this. There's another thing that people very often overlook. That is that the efficiency of a solar cell, any given solar cell, actually goes up enormously with the solar power incident on it. So when this is just to show that if how much current can I get out of a specific device. If I illuminate with 120 watts per square meter, 188, 265 is just an example. Up in space, we have 1340 watts per square meter, but it goes up also after that. So if you can make a solar cell that is able to keep itself cold enough, then you can actually up the efficiency all the way up to 70% for the same solar cell, pushing 100% if you can get the solar insolation, the solar power up a factor of 100. Of course, it will melt standard cells, but I'm just saying that theoretically, the loss will go down to almost nil. So solar concentrators would be a cheaper way to make the solar farm. So just to be able to make this best balance in the technology is one way that you get the future. The other one is ion motors. Right now, all the good ones are made out of the so-called Hall type thrusters. You can look it up on the web later on. What it is that you have an ionizer sitting here in the center, and then you put a cold stream in of gas. The ionizer is sending out fast electrons that are then ionizing the cold gas atoms. Then you have a huge voltage between the one end of the motor and the other, and you accelerate up the ions out here, and then you just let them pass a grid where you stop about 1% of the positive. The grid takes up some area. And then you have a stream of ions coming out here. You need a neutralizer to get this to work. But it's a relatively simple thing that was developed back in the 50s, actually. But it's only now getting into a reliability domain where this is good enough. All of those that they sell in the marketplace right now are running on a fuel, which is typically a heavy gas. Reason is that a heavy gas is easy to transport. You just have a pipe and then a valve, open, close, and then the motor will thrust more or less this way. There are so many other materials that can be used to be ionized. One of the easiest one would be just to use a rod of aluminum. And there's so much aluminum out there in the space debris. So a motor like this that runs on aluminum would just be a gift to the world for all the space debris, because then we can eat the old satellites, turn them into drive or to fuel for the existing satellites. So that's the technology that's also coming. It will come, just a matter of when. The communications is also a problem. It sounds stupid, but let me give you an example. I built this instrument that sits on this rover here some years ago, and is now driving around on Mars looking for life. When I got data here, I produce about 100 times more data than I can send to ground. The reason is that I need to send it from the rover to one of the orbiters up there, who has a big antenna that's pointed at the deep space antenna on Earth. And everybody produce too much data up here. So again, artificial intelligence would be nice to have. We do not have it. So we cannot send all data down. This little guy here, the Ingenuity helicopter, is flying around and it's actually a tech demo, because the next mission, the Mars Sample Return I just showed you, will not have a rover. It will actually have a giant helicopter that flies around and samples of this. So anybody dealing with helicopter designs also have a chance here. This is an emerging market. It doesn't exist yet, but it will be there. Robotics, typically in space debris handling, is also an interesting thing. Imagine that it means that you have to have grabbers and other things on board, none of which exist at this point in time, has never been tested. So also here, it's a big market here. But all of this takes communication, and safe communication is an issue for everybody here. We have simply too much data and too little bandwidth to it. And I put a little thing over here just to give you an idea of where I see the next big thing happening. That is, how can we assemble big space structures without the use of astronauts? We need to use robots. So we need to make things modular, and we need to make things expandable and serviceable by robots. And Lego is a very good example on this. I mean, everybody knows that a Lego brick can be used by a 5-year-old without any problems. This thinking has totally been lost in space. There are nobody that thinks about how can we link up many solar cells, for instance. Which structure shall they sit on? So that's another thing to go by. So if we now finally look at the space market as a sector, what is it to look out for? This is just a warning sheet. Don't do all the other stuff unless you're considered this. First of all, anything that has to do with space is enormously risk sensitive. So the first thing you need to sell to people is that there's low risk. It shall be sexy, but low risk. You will never come to sell large series of the stuff you're doing. If there was a large series to be had, it will be picked up by one of the bigger nations. Denmark will never stand a chance here, so be careful. Aim at stuff that has to be having a high knowledge content, that has to have high quality, but keep it at a low count. If you get up to the mass production, the other guys will eat you. Well, that might be very good if they pay you well, but it's dangerous. And mark you, there are both red and blue oceans all over the place. The funny thing is that it seems to be very, very random where you find the red and the blue oceans. So that's one thing to look out for. The market is growing, I would say, almost exploding these years. It's outrageously fast that the growth is. There are so many actors, so much demand. So what is it they say? In a growing market, everybody can survive. At least that's it. Time is good for you now with this. It's a controlled marketplace. Be careful. This means that many of the technologies that you could dream of doing might be deemed of national interest or be owned by the military or by some other guys. So it's not something that is, even though you have the world's best product, it might not be easy to sell to everybody. So be careful when you select a product for the market here. And you must be prepared to give a long-term support. As long as the mission flies, you need to support it. That doesn't matter how this is done, but that's it's not like a fast in, fast out of the market thing. You have to stay there. And that's also the only thing I can see. All our customers are pretty much returning customers or people that have heard about how fantastic DTU is supporting their friends out there in the market. There are many new customers, and when I say new, that could be Russian, Chinese, Indian. Be careful. Much of the stuff you're doing will be deemed dual use, and that means that it will be under export restrictions. So even though you think you can sell a lot of these to China, don't. don't forget to check whether it's under ITAR or EAR. Otherwise, you may end up in an orange suit in Guantanamo. But the thing to say is, the entire space market, it is dealing with the next generation of technologies. So I know that this was a speed tour through this. I should have had 3 hours more to get into each of these little subjects, but it's just to give you a feel for there's a lot of potential out there, and the market is open now. Don't sit on your hands. Give it your best shot, but take these things into consideration when you do so. So that's what I wanted to share with you today.
Thank you very much, John, and thank you for this look into the crystal ball of old/new space, so I can see at least a couple of concrete opportunities for Danish industry or Danish technology base in relation to the opportunities you described. So we also have a lot of Nordic participants or a number of Nordic participants today. And if you are inspired by some of this that John just presented, you should contact your your national ESA BIC manager to discuss opportunities for support in developing the ideas further. You may know we have the Nordic Launch Program, which is designed to do just that, to support ideas into developing into businesses in August next year. Thank you very much, everybody. Thank you, John, for this inspiring presentation. And we look forward to see you at the next ESA BIC Nordic Academy in the new year. But have a great Christmas and a Happy New Year from our side. And yeah, thank you very much, everybody.
Thank you.